People, welcome. How are you guys doing? I hope all of you guys are doing good and taking awesome care of yourselves and staying safe. And more importantly, I hope your preparations are going good as always. Okay, I can hear myself. So, yes, what is new in life? All good? Hello, how's your evening going? All awesome? Hi. Hello, Ji, kaise ho? All awesome, all good. Yes. All right, people. So, anyways, a very warm welcome to today's session. This is Vedantu's 9th and 10th English channel. My name is Anoop. I am your physics master teacher. Today, we'll be doing a lot of important questions because today is all about how can we, practice these questions of physics. Both from electricity as well as magnetism. So as you guys know, we have done a lot of series regarding the same. We have done the Sprint X series. We have done the top 20 questions. So this is basically a part of that where we'll be doing just practice questions and nothing else. So we'll take up one practice paper and try to solve these questions as fast and more importantly as precise as possible. So it's not going to be from one particular chapter. We've always followed that, like if it's electricity, just electricity, then if it's magnetism, then we just do magnetism. But today is not that. Today is going to be a kitty of all the topics, all the chapters. So it's like you can get questions from anywhere. Again, we have divided the questions into 2 mark, 3 mark and 5 mark questions. So yes, be ready. Make sure you put on the answer in the chat box and be super duper active. All right. So shall we begin today's session, people? Can I get oh yeah in the chat box if you guys are all ready? I hope you're able to hear me clearly, guys. I don't know if there's an echo or something like that. I hope everything is good. Just give me 1 second. Let me just check if the voice is clear. 1 sec. Let me just check if the voice is all clear and if there's no echo and stuff like that. Okay, no echo. Thank you. All right, so I just had to check that. I gotta check it. All right, because I don't want it to be like me miming. All right, it's like me talking and everything. It's like there are 10 Anoops in one room and talking to you guys. It should not be like that. Hi Priya, what's up? Hi Sneha. All right, guys. So without wasting much time, let's get into the topic. So we'll start with the 2 markers. Again, it's a practice paper for the year of 2022 because your exams are approaching really fast, and the more questions you practice, the more confidence you gain. So keeping that in mind, here is the first question of the day. The question is, a simple motor is made in a school laboratory. A coil of wire is mounted on an axle between the poles of a horseshoe magnet as illustrated. In the example above, coil ABCD is horizontal and the battery is connected as shown. Now the question is, for this position, the first one is for this position, state the direction of the force on the arm AB. We know that when a current carrying conductor is placed in a magnetic field, there is going to be a force, which is also known as the Lorentz force. Now the first part of the question is, if you were to take the arm AB, in what direction that force is going to act? That's the first part of the question, which is going to get you 1 mark. We are not done yet. The second part of the question is, why does the current in the arm BC do not contribute to the turning force on the coil? So let's start with the first question, which is quite simple. If I have to talk about arm AB, in what direction will that arm experience a force? Let's go, people. In the chat box, use whatever rule you have to, whatever hand rule you have to get me the answer. Absolutely, pakka, 100%, no doubt at all. Is there anyone else with a different answer? So much confidence in the chat box. Absolutely, people. There's going to be no doubt about this. It is going to be in the downward direction. Now, how do you figure that? Fleming's left hand rule. So if you would take your left hand and extend your fingers such a way that your thumb, index finger and middle finger are perpendicular to each other. The index finger shows the direction of the magnetic field, which in this case is going from west to east. The current is going into the page in the upward direction, that is towards the north. So your AB will experience a force in the downward direction. Super easy. Done. Now for the second part of the question, which states, why does BC, the arm BC, not contribute to the turning effect? How many of you guys know the answer for this one? Why does arm BC We know that AB is going in the downward direction. But what about BC? We know for a fact that BC does not take part in the turning effect. Now the question is, why is that so? Anyone who knows the answer for that? Very simple but important part of it, because while you're explaining the working of a motor, you also need to mention about this one as well. So how many of you guys know the right answer for this question? Let me know in the chat box. Come on guys, come on. Super easy question. Why does BC not take part in the turning effect? That is the question. Come on people, show me what you got. Show me the amazing Sherlocky brains of yours. Aha, Snehaji. Aha. Anyone else? Is there, everyone agrees with the same answer? Everyone is agreeing with that? Or is there any different answer that you guys have in mind about this? Pakka? 100%? 110%? 200%? Clear? Interesting guys? Absolutely correct. The reason why this happens is because guys, BC and the magnetic field, the magnetic field lines and the current, they are both parallel to each other. Since they're parallel to each other, the angle between the magnetic field and the current is zero. Now if you remember the Lorentz force wala formula, F is equal to BIL sine theta is the formula. Here it's sine 0, and sine 0 is nothing but 0. So BC and AD will not take part in the turning effect whatsoever. Why? Because the current and the magnetic field both are parallel to each other. See, magnetic field, the Lorentz force is maximum when magnetic field and current are perpendicular to each other. But if they're in the same direction, when they're parallel to each other, there'll be no force whatsoever. Why? Because the angle between them is 0. All right, that is the answer for that. All right, super important guys. While you're explaining the working of a motor, you also need to mention about this as well. All right, so please don't forget that. So it's important. You guys already know, I've told this a billion times already, working of a DC motor is very, very important for your board exams, because for sure you'll have questions from it. Either it might be asked as a 5-mark question or a 3-mark question or even a 2-mark question like this. All right, second question. What is an electromagnet? And write any 2 uses of an electromagnet. The second part though, you just have to look around you. You'll find tons of examples. You don't need to think about it too much. 2 examples are aram you can give. But what is an electromagnet? How would you define an electromagnet? Hi, Vanakkam Naveen. Hi, Azam. What's up? How are you doing? All right, come on, guys. What is an electromagnet? How would you define an electromagnet? Is the electromagnet a normal bar magnet? Is it a straight current carrying conductor? Aha, yes, Aishi. Exactly, guys, exactly. An electromagnet is nothing but when you take a soft iron core and put it inside a solenoid conducting, or you can say a circular coil, an insulated copper wire of a circular coil of insulated copper wire. What happens is that the iron core that is there, that is also getting magnetized because of the passage of current. This is what is called as an electromagnet. So electromagnets are nothing but the magnets that is formed by placing a soft iron core within a solenoid or a circular current carrying loop. This is what is called as an electromagnet, and this behaves like a magnet only when current is flowing through it. The minute the current stops flowing through it, it stops behaving like a magnet. So that is what is an electromagnet. So the major difference between an electromagnet and a permanent magnet is that in permanent magnet, the magnetism is not lost, but an electromagnet only behaves like a magnet when current flows through it. You have a lot of other differences also. In the case, if we talk about electromagnets, we can change the polarity, you can change the strength of it. None of that is possible with a permanent magnet. Over there, the magnetism is fixed, the polarity is fixed, but electromagnets, you can always mess around with the details of that. Okay, now tell me any 2 uses of electromagnet. Where all do we use electromagnets in our day-to-day life? Any answers of that? DC motor, absolutely. Motors, yes. DC motors, yeah. Any other answers? Motors in general, you could say motors in general, yes. Electric bells, The excellent example because you've already studied that in your lower grades. Absolutely wonderful. Anything else that you can think of? Fans, yeah. Basically, fan though will come under the category of electric motor. So yes, any other thing? MRI machines or MRI to lift heavy loads. Lift heavy loads, we use it to segregate, like in these dumping grounds, to segregate between iron and other material. Also, we use electromagnets. We use electromagnets in speakers. So the MagSafe of your iPhones and all that, all of those are also nothing but electromagnets itself. Those are not permanent magnets, but rather they're all electromagnets. So all of these are basically coming under the same category. All right, so that's the answer for that question, guys. Fantastic job. All of you guys answered really well. Moving on to the third question now. All right, so here's another one. Super easy. Again, it looks very big, but if you just look very carefully, you can see that this question also is divided into two parts, which means that each part carries 1 mark. So part A would carry 1 mark, also all the way till here, that would carry 1 mark, and part B would carry another set of marks. So here's the question. A circuit containing a battery, a variable resistor and a solenoid. The figure below shows a magnetic field pattern produced by the current in the solenoid. A. State how the magnetic field pattern indicates regions where the magnetic field is stronger. State how the magnetic field pattern indicates regions where the magnetic field is stronger. Second is, what happens to the magnetic field when the current in the circuit is reversed? So what you have is a very simple solenoid. First part of the question is, how does the magnetic field lines look like wherever the magnetic field is stronger? What does it look like? When you think about the magnetic field lines, what does it look like wherever the magnetic field is stronger? What does it look like? Oh, is it? Arey, awesome, Aditi. Congrats, Doug. Congrats. This is the mistake, guys. This is the mistake. Now, I knew majority would go with the same answer. I knew that majority would go with the exact same answer. Absolutely correct. See, wherever the magnetic field is stronger, the magnetic field lines will be more dense. It'll be more closer to each other. That's one thing. That's absolutely correct. There's no doubt about that. It's more denser. There's going to be a lot more magnetic field lines which are put together. It'll be very close to each other. But where is that? In a solenoid, where is the magnetic field the strongest? Where is it the strongest? In the magnetic, when you talk about a solenoid, where is the magnetic field line the strongest? Think about it. A lot of you guys are like, sir, near the poles. But no, that is not the case, people. Inside the solenoid is where the magnetic field lines are stronger in a solenoid. Just look at it. The magnetic field lines are more denser. They are more closer to each other inside the solenoid than the poles. Getting it? See, if you talk about a bar magnet, yes, I would totally agree with the answer that magnetic field lines are stronger near the poles. Absolutely, because you can't really see the magnetic field lines inside the bar magnet. But in a solenoid, the magnetic field lines are stronger inside the solenoid than the poles. Just look at the magnetic field lines, right? Here they're a little spaced, but inside they're very close to each other. Understanding? So inside the solenoid, the magnetic field lines are more stronger in the case of a solenoid. All right. This is the confusion that you need to get rid of. I know that a lot of you guys would have gone with the same answer. Why? Because several times you've been told that a solenoid's magnetic field lines are very similar to that of a bar magnet, and in a bar magnet, it's it's stronger near the poles. So here also it should make sense, but that is not the case, guys. Inside, it's going to be far more stronger. Why? Because you can actually see the magnetic field lines over there. All right. So that is the answer. Okay. Now to answer the second part of the question, what happens to the magnetic field when the current in the circuit is reversed? What would happen if you reverse it? If you reverse the direction, if you change the polarity, what would happen to the magnetic field lines? Think about it, guys. Very simple question again. Like jujube question. Uniform or strong? Piyush, inside the magnetic field lines are uniform and strong. Just because it's uniform does not mean that it is not strong, right? It's uniform and strong as well. All right. Exactly, guys. See, when you change the polarity of the battery, or you change the direction of current, the polarities would also change. Since the polarity changes, the direction of the magnetic field lines would also change. The direction of the direction, my handwriting is very clean, direction of the magnetic field lines will also change. Why? Because the polarity changes. Initially, let's say that this is the north, this is the south pole, and this is the north pole. When you change the direction of current, the polarity would change. Now this would become north and this would become south. So the direction of the magnetic field lines would also change. That's the answer. All right. So that is the end of the third question, guys. Fantastic job so far. But yes, regarding this, please don't get this wrong. Here also they've given the exact same answer, that the magnetic field lines are crowded around the ends, but that is not the case, people. Please remember that. Here also they've made the exact same mistakes. Inside the solenoid, the magnetic field line is the strongest. Inside a solenoid, that is where it's the strongest. But in a bar magnet, it's obviously near the poles. All right. With that said, let's go on to the fifth question. Now again, like I told you guys, it's going to be a mix of both magnetism and electricity. So few questions from electricity also we can expect. Here's one regarding the same. What is electrical resistivity? In a series electrical circuit comprising a resistor made up of a metallic wire, the ammeter reads 5 amperes. The read of the ampere decreases to half when the length of the wire is doubled. Why does that happen? First of all, tell me, what is resistivity? What is electrical resistivity? Acts as a bar magnet, but that's the thing, no, Naveen. That is what I'm trying to tell you. See, in a bar magnet is a solid structure. When you have a solid structure, for example, let's say, let's talk about this mouse. It's a solid structure. It's solid, which means it has a defined shape, it has a proper volume, everything is defined. The atoms and molecules are properly arranged. Can you actually put your finger inside the mouse? Can you actually see what's happening inside the mouse? It's not transparent, is it? Can you actually see what's happening on the inside? Can you exactly see how and what sort of, is it possible? No, it's not. So in a bar magnet being a solid structure, can you really see what the magnetic field lines are inside the bar magnet? Can you really see it? No, you can't, because it's a solid structure. You can't really experience it. That is why near the poles, the magnetic field lines are stronger for a bar magnet. But for a solenoid, on the other hand, the magnetic field lines you can experience because it's a hollow structure. So inside also there are magnetic field lines running through, right? So over there it will be far more stronger than the poles itself. Got it? I hope it's clear now. I hope it makes sense. Electrical resistivity is the resistance provided by the resistor having array. Amazing PhD, exactly. It is defined as the resistance offered by a conductor of unit length and unit cross-sectional area, such that the current flows perpendicular to the opposite faces. My God, Sneha. Electrical resistance, okay, yes. Absolutely, guys. Absolutely wonderful. Wonderful, guys. Wonderful. Amazing job. Excellent. Electrical resistivity is nothing but the resistance provided by a material of unit length and unit cross-section. It is nothing but a property of the material to provide resistance of unit length and unit cross-sectional area. That's all. So 1 meter or 1 centimeter length and 1 meter square area or 1 centimeter square area, cross-sectional area, the resistance provided by that material, that is what is called as resistivity. And this resistivity does not depend on any other factor other than the material itself. That's why it's a property of the material, because that is the only thing that it depends on. The material. What sort of material are you using? Are you using copper? Are you using iron? Are you using aluminum? What sort of material are you using? That is the only factor that it depends on. Resistivity depends on only that factor. Okay, now that you've answered that, let's talk about the second part of the question. You have a simple conductor and you've connected an ammeter to it. The ammeter reading of that conductor says 5 amperes. Now, if I increase the length of the conductor to double its original length, the ammeter reading decreases. Now, why does this happen? Why does that happen? Yeah, temperature also. Yes, Nipun. Temperature, absolutely yes, because when you increase the temperature, the randomness of the molecules would increase. They'll move more randomly. So that is also one more factor. Absolutely. Yeah, temperature also. Mention that also. Sorry, my bad. Thank you. Got it. Thank you. All right. Exactly, guys. Exactly. You know what happens when we know that resistance is directly proportional to the length of the conductor. So more the length of the conductor, more the resistance. So when you increase the length of the conductor twice of it, what would happen is that we know that current and resistance are inversely proportional to each other because of Ohm's law. from Ohm's law, we know that current and resistance is inversely proportional to each other. So since length and resistance are directly proportional, which means when you increase the length to double, the resistance also will become double. If the resistance is becoming double, current will obviously become half. So now that you've increased the length to double, the resistance will become double. Since the resistance is increasing by double, the current will become half of it. So that is the answer, all right? Because we know that according to the formula, R is equal to rho into L by A. This is the formula, right? Resistance is directly proportional to the resistivity. It's directly proportional to the length and inversely proportional to the area of cross section, all right? And that, my friends, is the fourth question. So we're halfway through now. Fifth question, on we go now. I hope it's clear so far. Any doubts so far, guys? Are you feeling confident? I can see that a lot of you guys are answering it perfectly right. There's no confusion whatsoever. But yes, if you are facing some sort of difficulty, please let me know so that I can help you guys. At the end of the day, we are here to help you guys out. So if there is a problem and you feel like you need a little bit more, clarity in a certain concept, let me know so that I can help you guys with that. No doubts. So should we write both the equations in board exams and show? It would be better if you could do this, because this way the examiner would find it easier to correct your paper because they know that you know the concept. So I would suggest you to write the formula as well, so that the equation, the relationship, so that it'll be easier for them to correct, and it's easy marks for you, so they don't have to go through the entire thing and look for spelling mistakes and all that. So this way you'll easily get the marks. All right, okay, let's go on to the fifth question, guys. Halfway through fifth question, here we go. How does the resistance of a wire change when the length is tripled, when the diameter is tripled, when the material is changed to one whose resistivity is 3 times? Okay, let's start with the first part of the question. It's a 3-mark question, so answer it very carefully. What would happen if the length is tripled? What would happen to the resistance if you increase the length by 3 times? Exactly, Anand. Exactly, people. Because we know that resistance is directly proportional to length. So if the length is increased by 3 times, your resistance will also increase 3 times. As simple as that, because they are directly proportional to each other. No confusion. Simple. That's it. No calculation, nothing. Just write this down and you're good to go. Okay. Second part of the question is, if your diameter is tripled, what would happen if you increase the diameter 3 times the original one? What would happen then? What would happen then? Arre, Piyush. R is divided by 3. Sure. Pakka. All right. Some of you guys are getting it right, but some of you guys are completely confused. Like, sir, it will decrease by 3. The answer is, guys, I'll tell you the answer. In 2 seconds. Let me see how many of you guys can answer this first. 1 by 27, 1 by 9, 1 by 3, 1 by 27. All right. So here's what happens, guys. See, we know that R is inversely proportional to area. Area is equal to pi r square, right? See, if you increase the diameter 3 times, the radius will also increase 3 times. Yes or no? If you increase the diameter, let's say you had a wire, the diameter was initially so and so. If you increase that 3 times, obviously the radius will also increase 3 times. So if I were to put this in this equation now, R is proportional to 1 by pi into 3r square. What will you get? R is equal to 1 by 9 r square pi, or you can say that R is proportional to 1 by 9th of the original area, because pi r square is what? It's nothing but area. Simple. So it's going to become 1 by 9th of the original resistance. Whatever was the resistance, it's going to become 9 times less of that. All right. So new resistance will be 1 by 9th of the original resistance. Got it? So do not get this wrong, because I know it's easy to make such silly mistakes, especially when it comes to this. It's very, very easy to get it wrong, but please do pay attention to all these smaller details. So diameter, when you triple it, the resistance becomes 9 times less than the original resistance. Okay, now that is out of the picture, let's go on to the last and the final question, which is nothing but what, guys? What would happen if you change the material to another material whose resistivity is 3 times the original one? Then what would happen to the resistance? Pata tha Piyush ji? and still got it wrong. Huh? Oh, is it? All right. It's okay. Oh, me a challenge. Huh? So much confidence. Huh? So much confidence. Confidence is oozing out of your face now. 3 times exactly, people, because we know that what resistance is inversely directly proportional to resistivity. So if your resistivity is increasing 3 times, resistance will also increase 3 times. As simple as that. So that is the answer for this question, guys. And that marks the end of the 2 markers. I believe this question should have been a 3 marker. It's definitely not a 2 marker. Each part would carry 1 mark. So I'm guessing that, you can, if this ever comes, this would generally come for 3 marks, all right, not for 2 marks. All right, but that's it, guys. Let's go on to the 3 markers now. All right, 3 markers, again, same deal. You'll have a mix of both magnetic effects as well as electricity. Try your best to be as detailed, as precise as possible. But again, you don't have to write the entire story. Keep it short, keep it simple, because at the end of the day, it's not an English paper, it's a physics paper. So keep all the relevant terms in the answers that you give. But more importantly, make sure you stick to the point. So here's the first one. Calculate the total resistance of the circuit and find the total current in the circuit. You have to find out the total resistance first, and at the same time you should also find out what is the total current flowing through the circuit. So let's start with the first part of the question, which is nothing but finding out the total resistance. Let's start with the total resistance part of it. Okay, now tell me, people, let me just make the video go on this side. I don't know if you guys can see the question now. Let me just see if you can see it or not. I just need some okay, the question is covered now. Okay, so I'll just switch back to this one itself. All right. Okay, so here's the thing, guys. First of all, tell me which of these are in series and which of these are in parallel. Let's start with R3 and R4. R3 and R4, okay, all of you guys already 12. Wow, bete, wow. My God, people. Question is already covered. All right, then I don't think I need to, okay, I'll just quickly finish it off then. So R3 and R4 are in series, people. So first of all, write that R34 is equal to 6 plus 4, which is equal to 10 ohms. Now that you've solved that, we would see that these two are, once you've solved this is nothing but 10 ohms. So these two are parallel, so solve for that. So 1 by R234 is equal to 1 by 10 plus 1 by 10, which is equal to 2 by 10, which is R234 is equal to 10 by 2, do not forget to reciprocate, so it's going to be 5 ohms. So 5 plus 7 is the total resistance, so R1, 2, 3, 4 is equal to 5 plus 7, which is equal to 12 ohms. Absolutely correct. So that is basically the total current. Now to talk about, total resistance, to talk about the total current, we know that I is equal to V by R equivalent, my bad, sorry guys. I is equal to V by R equivalent. So write that down, substitute the values and get the answer. So the total voltage is 24 volts and the total resistance is 12 to 24. So 2 amperes would be the answer. Super easy. That's all. This is a super duper easy question. But again, guys, in your exams also, you can expect one level more difficult than this. So be sure to practice as many number of circuit diagrams as possible, because for sure, once again, you will have questions based on circuit diagrams. Absolutely 100% you'll have at least 1 or 2 questions. So be sure to practice as many questions as possible. All right. So in the meantime, guys, read this other question. This is the 8th question. So much better. All right. Shruti draws magnetic field lines close to the axis of a current carrying circular loop. As she moves away from the center of the circular loop, she observes that the line kept on diverging. Explain the reason for her observation and write 2 properties of magnetic field lines. Let's start with the first part of the question. Shruti draws a magnetic field lines. Awesome, Shruti. Good for you. Close to the axis of a circular current carrying loop. So you have a circular current carrying loop and she actually drew out the magnetic field lines. Now what she noticed was that as she moved towards the center, the magnetic field lines kept on diverging. Now what could be the possible reason as to why this happens? Come on, guys. Yes, Sherwin, we did. Unfortunately, yes. Hi now, what's up? Oh, is it? Oh, okay, sir has already done this in 10 most important question. Exactly, Anand. Yes, Aditi, please put on your doubts. Exactly, guys. What happens is, guys, see, we know that when see, near the conductor, the magnetic field is going to be the strongest. Near the, you know, near the conductor, the magnetic field is going to be much more stronger. It's going to be the strongest there. But as you go further and further away, the magnetic field lines get weaker and weaker. Because of that reason, you see that the magnetic field lines are diverging. There's a lot more space between the magnetic field lines. Why? Because the magnetic field is getting weaker and weaker. And as you reach the center, you're going to get a straight line. Why? Because the magnetic field line now has become uniform. This is the reason why this happens. Now, to answer the second part of the question, I hope it's clear, because it gets weaker. The magnetic field lines get weaker and weaker as you go towards the center. Okay, second question. Give any two properties of magnetic field lines. Exactly. It is decreasing. Exactly. Hi, Harmanjoti. What's up? I'm good. How are you doing? How are your preparations going there? They are closed curves. Okay, you can say that. Magnetic field lines of a bar magnet is closed curves. Absolutely correct. They are closed curves. Because again, it's not, if you talk about straight current carrying conductor, it's going to be concentric circles. If you talk about, solenoid, it's going to be similar to that of a bar magnet. So in a bar magnet, if you have to mention that in a bar magnet, the magnetic field lines are closed curves. They are actually closed curves. Okay. Any other property that you can think of? Exactly, guys. They do not intersect with each other. No two magnetic field lines of the same magnet would ever intersect each other, because if that ever to happen, physically, when you keep a magnetic compass over there, you would have two different north poles, which is not at all possible. And hence, you can mention that one as well. So that is, yeah, you can also mention that one. Yeah, wherever the magnetic field lines are stronger, it's going to be more dense, it's going to be more crowded. Wherever it's weaker, it's going to be well spaced apart. Now, any two properties is absolutely fine. So the choice is yours. It's completely up to you guys. And yeah, you can also mention this, that they originate from the North Pole and end up in the South Pole. So any of these two, any of the points that you can mention, they've asked for two. So any 2 points would absolutely fetch you the marks. Okay. Almost towards the end. 9th question, people. 9th question. We are almost done. We are at the end of it. So here's one. Draw the pattern of magnetic field lines around a current carrying straight conductor. And how does the strength of the magnetic field produced changes with the distance from the conductor and when an increase in current in the conductor? Let's go. Okay. First of all, what does the magnetic field lines look like around a straight current carrying conductor? Absolutely, they are nothing but concentric circles. Around a straight current carrying conductor, it's going to be concentric circles, nothing else. Concentric only forever, that's all. Now, the question is, what would happen to it as you go further away from the conductor? Exactly. As you go further away, the magnetic field would become weaker. It'll become weaker as you go further away. That's exactly what happens. Okay, second part of the question. What would happen if you were to increase the current flowing through the straight current carrying conductor? Exactly, guys. The magnetic field would now increase, because why? Magnetic field is directly proportional to the current flowing through the conductor. So greater the current, greater the strength of the magnetic field as well. That's it. All right, guys. That's the end of the 3 markers. Let me ask you a simple question. Is everything clear so far? Feeling a little confident? Yeah? All good so far? Absolutely, guys. Wonderful job. First of all, a big round of applause to all of you guys, because you're doing a fantastic job. I pretty much got I got every single answers from you guys. I didn't have to put in a lot of effort. So it's all you guys. You guys are the stars for today's session. Absolutely fantastic job. Keep up the good work. Keep practicing as much as possible. I know that a lot of questions were repeated because it's only 2 chapters, guys. There's not much we can do. We have to create our own questions now. There's nothing else we can do. We have to make up our own questions. We have to make up our own concepts. So I'll start with Fleming's left-hand rule, if I have to, or Anoop's left-hand rule. I have to make up with my own concepts now. Fleming's, what is that? Leg rule I have to start now, or Anoop's leg rule I have to start now, where the what is that? The toe points in the direction of current. I have to make my own rule. That's all I can do right now, because we have pretty much done everything. Hip rotation rule, that's another one that we can do. Hand rotation rule, that's another one that we can do. But apart from that, though, there's really nothing we can ask, because it's a very small topic. We have 2 chapters and there's only so much questions we can possibly ask from that. So yeah. Okay, so let's go on to the 5 markers now and let's call it a day. Here is a 5-mark question, guys. A little different from what we generally do. I really love this question. So please give your best in this one. Ansari sir. Okay, Ansari Sarji. Ansari Sarji was demonstrating an experiment in his class with the setup as shown in the figure. So you can see the setup for yourself. There's a spring, there's a moving magnet, there's a stationary coil, and there's a galvanometer connected to the stationary coil. You guys know what this is, all right? You know what this is. All right, so this is the question, guys. Very small, teeny tiny question, just 1 page, that's all, nothing much. It's just 1 full page, like jujube question. No, it's like a small question. Like obviously, you've been, you've been skating through life all this while. So we decided why. We have to, why not? Why not? So here's the question. A magnet is attached to a spring. The magnet can go in and out of the stationary coil. So because of the spring, right, the magnet is allowed to go back and forth, up and down. If he lifted the magnet and released it to make it oscillate through the coil. So he pulled it up first and then let it go so that the magnet can move up and down. Based on the understanding of the phenomena, answer the following question. What is the principle which Ansari Sarji is trying to demonstrate in this experiment? What is the principle? What is this principle called as? Exactly, my friends and colleagues, ladies and gentlemen. Exactly, it is. Please ignore. Instead of writing electromagnetic, I was going to write electromagnetic. Yeah, that's a new phenomenon that I invented today. Electromagnetic. I wrote a G there. I'm telling you, this is what happens when you have autocorrect and Grammarly with you all the time. Every wrong spelling that I type on the phone, it automatically gets corrected. So I've been spoiled by this now that I'm expecting someone to correct it automatically. Anyways, electromagnetic induction is what it's called as. Wonderful, also known as EMI. Fantastic. Okay, next part. What will be observed if the magnet starts oscillating through the coil, and give reason behind the observation? What would you see if this magnet moves back and forth? What is that thing that happens when this magnet moves back and forth? Yes, I will not. Why? क्यों हंसो मत, हम हंसेंगे, हमरा हंसी तो वायरल होगा. Exactly, guys, exactly. There's a current being induced. There's a current induced because of the movement of the magnet. So what happens is that there's going to be a deflection of the magnetic, the galvanometer. There's going to be a deflection. There's going to be a momentary deflection in the galvanometer as and when the magnet is moving. Absolutely correct. The reason behind this is because of electromagnetic induction. When a moving magnetic field is linked to a conductor, there's a current induced, and that is the reason for it. All right. Last question, guys. Consider the situation where the magnet goes in and out of the coil. State any 2 changes which could be made to increase the deflection of the galvanometer. What can you do? Any 2 things that you can probably think of or possibly think of which can actually increase the deflection of the galvanometer. Absolutely, guys. Increase the speed. You increase the speed at which the magnet is moving. The more faster it's oscillating, the more current is going to be induced. That's one thing. Anything else that you can think of which can actually increase the amount of deflection or amount of induced current? Anything else that you can think of? Exactly, guys, exactly. So there are 3 things in total. One is increasing the speed. The other is bringing or placing a stronger magnet. a much stronger magnet, because the stronger the magnetic field, the more the current induces. But last but not the least, guys, you can also increase the number of turns as well. So the longer the conductor, the more the current is going to be induced. So any of these three things can happen or can be changed in order to increase the deflection in the coil. All right, so that marks the end of today's session, guys. That's all for today. But yes, keep practicing, keep keep solving new questions, and keep keep yourself active, and make sure you keep going back to the concepts over and over again, so you don't ever forget this, even if you want to, right? So keep going back, keep going through the questions and stuff like that. And yes, do not forget to like, share, subscribe. I'll just stop it over here. That's all from my side. If you have any doubts, you can let me know right now. But yes, you can, if you want to reach out to me, guys, you can reach out to me on Instagram. This is my Instagram handle. It's Anoop_Vedantu. And if you want to reach out, send a mail, it's anoop.manoharan@vedantu.com. All right, so that's pretty much it, people. Singing a song. Can we end by singing a song? Why not? Twinkle, twinkle, little star, how I wonder what you are. Up above the world so high, like a diamond in the sky. Peace. That's all. I know. Don't clap for me. I'm telling you, if I see this, if I were to sing this and make a album out of it, I would have probably gotten a Grammy award for this. But I'm not doing this because I just not want to become famous. I just want to stay a teacher. I just don't want to become like Post Malone with a tattoo on my face. That's why. Getting it? I'm too cool for that. All right. So yes, that's all for today. I know, right? I know. I'm very humble like this. I know. I'm like, see, who do you think Kendrick Lamar got inspired from to write that song? You're looking at that person. Okay, the person now. But I don't take credits for all this. I don't take credits for all this. Because, again, I'm too humble. Too humble. See, I drink normal water from a normal plastic bottle. I'm too humble. क्या करें? हम तो है ही ऐसा. क्या करें? हम तो change नहीं होंगे. No matter how much, how much I grow, I always stay humble. Thank you. I know, right? I know. That's why every day I wake up in the morning, I take some, what is it called, as a dried chili, like do this to myself and throw it, because nazar na lag jaye. That's why. I do a lot of stuff like that. All right? Every time I wake up in the morning, I look at myself in the mirror. I'm like, wow, Anoop. Wow. Nazar na lag jaye. Do 3 times, throw it. All right. So anyways, guys, enough. Too much. All right, so that's all for today. Enough self-praising. I know. Too much. So yeah, guys, anyways, have a wonderful day. And I know. It's not overreaction. This is underreaction. Overreaction would have been Abhishek sir. This is underreaction. This is me. Overreaction is Abhishek sir's. This is underreaction. I know. Exactly. Anyways, guys, take care of yourselves. All the best. You also start doing it so that nazar na lag jaye. Every time you wake up in the morning, take a couple of dried chili, light a fire, and then just do this so that nobody looks at you and goes, "Oh, humko bhi Naveen ki tarah banna hai." So that they don't put nazar on you. All right, do it. I'm telling you, it works. There's a science behind it. If it starts burning, that means nazar lag gaya already. Just kidding. Don't follow all of that. Anyways, just focus on your studies, guys. Focus on your studies. We'll be coming up with lots of amazing stuff. There's a lot of good stuff coming. Lots of fun, super amazing stuff coming up pretty soon. So do not forget to subscribe. I'm actually very excited for the next month because there's so many super amazing stuff. Trust me. You would love it. You would enjoy it. So do not forget to subscribe to the channel. Hit the bell icon just for the sake of it. And be sure to spread the word. All right. I'll catch you guys in the next one. Take care of yourselves. Stay safe. Have a fantastic day ahead. Have a brilliant day ahead. All the very best of luck. And stay safe. Stay happy. Stay chill. Peace. Take care, guys. Bye-bye.